Hello everyone, Namaste. I am Ramnath who would like to present you the key learnings from chip development. This is part 9. This is on synthesis of RTL design. This is continuation of part 8. And during this presentation, I will be mainly touching on design rule checking and what gets changed as part of the design. This is basically preliminary details only. For more information, please feel free to refer to the references. Lot of material exists on the net. Thanks for learning along with me. Feel free to provide your suggestions. As in the earlier part 8, we have known that during the synthesis, RTL design is considered, and aside to that, standard cell library, memories, IOs, analog blocks for the specific technology is considered, and technology specific design constraints are considered, and during that phase, RTL parsing and elaboration, technology mapping, design rule checking, logic optimization will be done. We will be learning more on the design rule checking part. Okay. At this step where design rule checking is about to be performed, we assume that the RTL parsing and the elaboration step has been completed. Hence, the RTL has been converted into general gates. Since technology mapping has also been completed, now the design has been mapped to the respective standard cells with the different possibilities when with respect to specific technology targeted. The other IPs are also present. So now this design, especially in terms of the digital design, it is ready with all the necessary contents, because the RTL is now converted into the gates, which can be ready for the fabrication. However, this design at this point of time, since this further processing has not been done, it will be very prone to crosstalk, because there will be huge loads on some nets, which will lead to uh, low signal strength, and hence it will have multiple glitches and prone to crosstalk. In other way also, because its slow degradation will be so bad on some nets that power consumption will also be high. So these steps will be resolved during the design rule checking phase. So we will be analyzing, see in this case, a portion of the circuit to illustrate the benefit of design rule checking. Okay, here maximum transition, maximum capacitance, and fan out also, but fan out is indirectly now covered as part of the maximum capacitance. So we will be figuring out how we will be smoothly controlling the net capacitance, so that the transition time from each standard cell will be within the limits at which the design standard library is created. That is the main aim of it. We will see how it is done. In this case, let us analyze this portion of the circuit. Okay, this portion, and let us analyze this part. Okay, so if you observe closely, this highlighted pink color, sorry, purple. So what happens is, like, this XOR is driving this net, this one, and it has input pin capacitance. It has two fan out because it is driving two cells. Okay, so it will have the load. This will see a load of this much wire length, this much wire length. Aside to that, the input pin capacitance of this cell and input pin capacitance of this pin. Okay, so this whole thing acts as a load. At the moment, let us consider they are within the limits. Okay, now if you see this circuit which we are analyzing, okay, for simplicity I have considered the other input, which is this one, to be 0. Okay, now done with this net, whatever, and the associated capacitance, the whole thing is represented in a lumped format in RNC. However, in the actual spec file, which is the standard parasitic extraction format, which is the representation of the nets, you will observe that it will be distributed a resistor and capacitor. Okay, so that is the advantage of it. So this for cell, and this net is represented by R and C, and this is the output. Okay, how the transition change. So we will be seeing. So the input of this cell, assume that it is coming in this format. Okay, assume this cell, this output is 0, okay, as specified here. So now the output of this transition, that means input of this XOR, is in this way. Okay, so transition time is usually compared, checked between 20% to 80%. What is this much? Okay, this is in voltage, this is time. Okay, during this time, how quickly it can reach from 20% to 80%. So if this is the input transition time, then what will be the resulting output transition time of this cell with this load? So what we will be checking is, like we will be checking will be considering the input transition and the output to load of this cell, and then we will figure out what is the uh, output transition of this cell. For this cell, for this purpose, we will use um, the, the dot-lib view to estimate this transition. So if you see say this is one hacked dot-lib which I got it from net, and then I'm showing here. So some flaws may be there. I try to adjust a few of them. So this is the output pin, assume Y, and what happens is, like, the main important ones I will be touching. The rest you can figure out through the Liberty or manual. So here the function name and everything is mentioned, and aside to that, if you closely observe, you will observe that the cell rise delay will be mentioned. How quickly the pin Y, the output pin, will be rising. Okay, based on the input. Okay, so here to figure out that, the standard cell will be characterized. So during this characterization, it will be taking the different input transition as demarcated by index 1, and by considering the different load conditions, index 2 will be considered. Different values will be considered. Based on that, the rise delay will be considered here. Okay, so the rise delay, how we will be getting is basically through 50% of the input to 50% of the output. What is the difference time wise? That time will be mentioned here. That means, like, if in the case of one index 1 first value, and output output capacitance value of 1. Wow. So 50%, what is 50%? What is the 50% value? If you figure out that value, delay value is represented by the first value. So this whole value will be represented by the first value of the index, and the second value, like that. So each transition and load, how they will be taken for this entire uh, table, delay table will be mentioned. However, in the actual, uh, uh, this is all used mainly for the manual purpose, but the tool actually does not use this simplistic model now, because this is a very simplistic model, and this is mainly useful for manual analysis purpose. Okay, tools generally use complicated models, so CCS models and all. So you can get more details from it. So they will be taking the voltage model, and then based on that voltage time, and then afterwards they will be figuring out in the current, and then figuring out what is the delay. It is bit more complicated. Okay, for understanding purpose, this is very easy, so we will take this one. So this is how the delay is calculated. Now what happens is like, so the rise transition is also calculated because I'm not able to see well. So I'm not able to point out exactly. So this is the rise transition. So here same index 1 and the index 2, whatever is mentioned, the same things are used and the values will be specified. Just like this, the corresponding uh, output transition values are also mentioned here. Okay, here it is not shown. Thus, for different input transition and output load situations, the delay values are mentioned, in this case cell rise, and rise transition values 20% to 80%, what is the value, it will be mentioned here, not shown. So based on these data, the tool will evaluate what would be the output transition value. Okay, how that will be later used as part of the design rule checking. Okay, in this case what happens is like, assume the load value is second value 0.05 here. Okay, then what happens is like, and the input transition is say 2. Okay, 2 and 2, so you will figure out that this is the value at this point. Okay, so this is the delay, and similarly transition is corresponding to 2 and 2, what is the values, that specific value, that value will be coming. However, you will note that the these values, this load value, which is the load of this net, is well within the limits of this library of this cell. So the maximum capacitance as characterized by this cell is 0.6. So it will be able to figure out even the rise transition also. So maximum transition is not crossing because the transition at this point of time is 0.18 and the load is 0.05. However, if by some reason, if this load of this net changes, then like it becomes more for some reason. Okay, then how will it figure out? Then what will happen? So that is the main point we are discussing. That means like the slew becomes very large. If you see here, the net became very large. It is just shown in a different form. So you will see that the R and C became large. However, this cell is same. So what happens is like, the output transition time will be large. Assume it is 0.6. Then you will figure out that the for information sake, I will talk about the delay because the rise transition data is not there. So you will figure out that 50% of input to 50% of output value will be large. Okay, so assume that same input transition 0.18, and then if you observe, the value will be large, so delay will be large because now the cell is taking a longer time. So that is why you will figure out, this is same thing like if you take the RC component, this is the step function, it will grow in an exponential manner. Okay, so same concept what we have studied earlier in BTech. So same thing, it will be growing exponentially but very slowly because now the RC time constant increased drastically, hence it is taking a longer time. So what I want to mention here is like, the time taken to reach it is longer. Hence, this is now becoming a very easy target. That means like it will become a very easy victim net. Because of this victim net, and if by any chance it is going to the reset pin of a flip-flop, then it can easily knock out and it can easily trip, and then it will create unnecessary zeros when it is supposed to be not creating it. Okay, so those things we need to avoid. Otherwise, this design is as good as ready for shipment. So what we will do is like we will figure out now there should be some mechanism because this much long transition is not should not be should be avoided. So how will we figure out? So if you see here, then we should figure out mechanism. How we will they have figured out in the ancient times we will discuss. Okay, because the same things they have already so many different situations people have already addressed these situations. We will come to that. In the ancient times, if you observed, people were also pushing large stones and all, and it was so difficult for one man to push this from bottom to the top. It will be highly risky and it will lead to huge stress on this person. So they have devised already how to resolve this one. They have used sometimes animals and sometimes many people doing and then pushing large blocks. And in the same way, different areas they used different schemes to push the very large objects. Okay, these are all stone objects. So these people were all pulling in a rhythmic manner. So these same concepts, even synthesis tool will also use to solve the large loads. Otherwise, this problem will become a reliability concern. Let's now go back to the previous step. Okay. So here we are observing the mm, same circuit, which is the portion of it, and we wanted to see what will happen if the net load becomes larger. So that is the main thing. So we have observed that now the net load became larger and the R and C became huge. So now there are different possibilities. That means like because now what happens is like this is the zero point 0.6 say unit of the load, whatever is seen here. This is the index 2 is the load. So if that load becomes larger now, because this is now larger, then as mentioned earlier, this is getting degraded. So this we need to prevent. So what we have possibilities is like we can increase the drive strength of this cell. That is one method. Another thing is like we can add some extra buffers on this network. That means like we can add some buffers here, some buffers here, some buffers here, based on the need. So that way, what happens is like this slew on this network that will improve, and on this network it will improve. So whether one buffer is used to be used here or no buffers here, that all depends upon how much these nets depend upon and how much they contribute the load. So definitely that means like what is the input pin capacitance of this, and if at all in some cases there are more fan outs. So this net and this net need to be handled uniquely and differently. And whether we need to increase this drive strength or add buffers here, that also depends based on the optimal selection of the design. So for that again the power, area and performance all come into play. So that is why the design rule constraints play a great role in each step, and then they will be guiding the synthesis tool to take right calls. So what happens is like, so in this case, the maximum capacitance of this cell is so and so. If you see, this is the output pin. That means like this cell, just like a man says, like assume I can carry or push uh, around say 50 kgs or 80 kgs, something like that. That is specified here, maximum capacitance. So more than that, I cannot drive well. That means like if I give me more load than that, then my transition will suffer. That means like my 20% to 80% transition suffers. Hence, the 50% line will be differing. So the output delay, the transition delay will be larger. So we need to arrest that one. So what we need to do is like the tool will take different calls. It will iterate on let us increase the drive strength of this cell and figure out. That means like there will be in the standard cell library, there will be multiple cell possibilities available. That means like as we have seen in the earlier slides, like there are VT modifications possible. That means like instead of making it into HVT, we can make it into LVT and increase the uh, uh, better, make the better transition time and reduce the delay. Or sometimes by keeping assume that instead of keeping the changing the VT, assume we can change the length. That means like large length of a devices to small length of devices. Sometimes what happens is like in the same technology there will be multiple channel length offering possible. So sometimes no, the design will be done with the large gate length initially. Then they can pick the small gate length XR. That is possible. And another way is like keeping the VT channel length same. They will increase the drive strength of this XR. That means like they will change it to X4, X8, X16 based on the different drivabilities possible. Thus, the tool will figure out what is the optimal approach for so and so load. There is another possibility is like instead of assume that that is not the optimal solution which the tool thinks, then it will think like let me keep this drive strength as it is, because for this and this by combining it, maybe let me put some drives additional buffers here, and then we'll be able to drive this net properly. So it will figure out that this load is larger, this section of the load compared to this one. Then let me add more buffers in this part compared to this one, or vice versa, based on the situation. So it will take those calls and it will improve finally the incoming transition time for this cell. Similarly, for the in this cell, the incoming transition time, that means like output transition of this cell, assume that there are some more cells, then finally it reaches that incoming transition time will be better, and it is falling within this table, index 1 line of the other cell, this cell or this cell we are talking. That is how this the design rule checking phase will alter the maximum load on the nets and improves the reliability of the design. Okay, we will see how these things will have ramifications on the design spec. Okay, in one situation where the input design has large input large load, then the synthesis tool could have done somewhat in this fashion. That means like it has added some buffers in this asymmetric manner. It need not be symmetric like add two here, add two here like that. It has already evaluated which will be the better option. Okay, so this is one part of how manipulation which is possible in the design rule checking. Thank you. Feel free to refer to the references as well.